Hi, in this video we continue the study of the notion of differentiability of curves. As we said in the previous video, we work with differentiable plane or space parametrized curves. For example, for a space curve we have a function taking values in R3, so that the function has three components. To compute the derivative, one just computes the derivative of each of the components using the rules of derivatives of a basic course on calculus. And very important, that derivative is a tangent vector to the trace of the curve at that point. Then, we can easily build the tangent line to the trace of a curve. For example, for a plane curve, at certain point alpha of t, the parametric equation of that tangent line is that point plus parameter the derivative. With that point and that vector, we also have the continuous equation of that tangent line, or the implicit equation of the tangent line. For space curves, we also have the parametric equation, in the same way, point plus parameter and the tangent vector, the derivative. We also have the continuous equation with that point and that vector. In the previous video we had an image of a plane curve and the derivative, and we checked that that derivative was tangent to the trace. We now have an image of the three-dimensional curve, a space curve, the helix, and a derivative. If we rotate the image, we check that that derivative, the red vector, is tangent to the trace. But be careful, the previous definitions of the tangent line requires a non-vanishing derivative. This fact motivates the following definition. The values t for which the derivative doesn't vanish are called regular, whereas those values for which the derivative vanishes are called singular. The following examples will illustrate the classification of regular and singular points given before. We begin with the parametrization of an ellipse, of which you have the expression of the curve and the derivative on the screen. For example, for t equals p over 4, these are the values of the parametrized curve, that is, a point of its trace, and the derivative. They provide the tangent line to that ellipse at that point. The continuous equation is on the screen. In the second example, we work with other parametrized plane curve, the cycloid. You have both the expression of the curve and the derivative on the screen. For t equals 2 pi, that derivative vanishes. We cannot give the tangent line to the trace of the curve at that point in the same way we did before. This is a singular point. It is actually a cusp. We now give an interpretation of the derivatives of a parametrization of a curve. The first derivative can be seen as the velocity vector of that parametrization. If we use the example of the rail line joining Madrid and Barcelona, for every value t of our trip, time, the point will be in the trajectory, and the derivative will consist of a vector tangent to the trajectory, and the length of it will be the speed of our trip at that point, say 300 km per hour, for example. With respect to the second derivative, this one can be seen as the acceleration vector of the trajectory. For example, in the image of the ellipse you have on the screen, the first derivative is the red vector, the tangent vector. The green vector is the second derivative, the acceleration. We can now decompose that acceleration into the tangent and normal or perpendicular parts. The tangent part changes the speed of the trajectory, but the normal part bends the trajectory. This idea will be connected with the notion of curvature in a subsequent video. We end this video with a remark. We know that the same trace can be defined from different parametrized curves. These different parametrizations will define different tangent vectors, but all of them will give the same tangent line.